All right, so here's problem number 29 from 3.5. And it's our classic problem. We're given a curve and we're asked to find the tangent and the normal. To do the tangent, we're going to need the tangent slope and a point. But they already gave us a point, so all we need to do is go to the slope first. Let's get to the slope by calculating dy dx. That's going to be root 2 times negative sine of x, or negative root 2 times sine x. So far, so good. The tangent line slope, m, is going to be the value of dy dx when x is equal to pi over 4, which is going to equal negative root 2 sine of pi over 4, which is negative root 2. And what is the sine of pi over 4? I cheat by drawing my reference triangle. Opposite over hypotenuse, it is 1 over root 2, or root 2 over 2 if you are into rationalizing the denominators. It looks like the slope is negative 1. So, taking this information and our point together, we're going to find that the tangent line is y equals the slope of negative 1 times the quantity x minus pi over 4 plus the y value of 1. And then, unfortunately, that's not the answer they give you in the back of the book. So you say, okay, what if I distribute the negative 1? I get negative x plus pi over 4 plus 1, and that's the answer that they have in the back of the book.
And anyway, could a line or some sort of I don't know, parabola with a value of pi over 4, could pi function as some sort of variable, or is it a constant?
Pi is a constant. Pi is pi. Right? How about the normal line? It's going to be y. Instead of negative 1, we're going to do the negative reciprocal of negative 1, which is 1. Again, minus x1 plus y1, or it is x minus pi over 4 plus 1. And probably supporting this graphically is a great idea. Probably. Well, let me start my calculator. It's going to take a while. All right. So Charlie, after you calibrate my board, remind me to start my calculator so we don't ever have to wait for the calculator to start, okay? Okay. All right. So our original equation, we're going to put into y1. And that was what? Square root of 2 times cosine of x. And then we're going to put the normal, let's say the tangent curve. And that one, and we'll put the normal curve, or the normal line here, and let's zoom normal, and let's see what we get. And how do we do? Does it look like it's tangent to the curve?
Yes. See the square.
And second, trace at what? Pi over 4? Pi over 4. Oops, I did the wrong thing. Didn't I? Trace, second, pi over 4. Oh, this is like a tragedy. Trace. Second, 1 there. And then we go over into the second curve. Second pi over 4. It's 1 on the, that's the normal curve. And then lastly, there's the tangent curve. Second pi over 4. And that's all. So it looks like it's tangent. It's definitely going through the right point. I think we got it. All right. So there's 29. What do you want to do next? 37. 37. We've got a function, g of x. And that function is defined piecewise. Just before getting to 0, it's linear. And just after 0, it's cosine. And we want to know, for what value of b can we make this continuous? And then, is it differentiable? Well, in order for it to be continuous, x plus b is continuous, right? Cosine is continuous. The only place it might not be continuous is where these two meet up. So what happens? Can we make those two equal at the point at which they cross? Cosine of 0 is 1. So if b is 1, this function will be continuous.
Wait, how did you know to do that?
Because the only place it might not be continuous is where the two pieces come together. So I have to make them output the same value as they approach 0. So I'm making these two things equal, and then I'm saying I'm only interested in what happens when they get to 0. Replace the x with 0, replace the x with 0. I think we actually had a problem in the chapter 2 test exactly like this. Did we? Yeah. Same idea. All right? Now, second question. Is it differentiable? In order for it to be differentiable, both of these two pieces are going to have the same derivative as they approach 0. Well, what is the slope of this, the negative part, as we get closer and closer to 0?
1.
The slope is equal to 1 as we approach 0 from the left-hand side. What about approaching from the right-hand side? Well, its slope is being determined by the derivative of cosine of x, which is sine of x, and this value at 0 is 0. Are these two slopes equal? So if we force b equal to 1, we get a function that's continuous but not differentiable at 0. And that's how we do that problem. Yeah?
I did kind of similar way. I figured out what it'd have to be so it could be continuous, and then I did what it should be when it could be differentiable, and I said they don't equal. Is that okay? I just said the b values would be different. One would be 1 and one would be negative.
Well, I can't think of any b value that's going to change the slope here. This top part is going to have a slope of 1 no matter what b's value is.
Would it be 1 over x? Because then you get, no, not 1 over x, negative x. But then that
This?
Yeah.
Wait, the derivative with respect to x of x plus b.
But then that'd be 0. It would just be.
No, the derivative of this is 1. Now, if you want to think of this as,
Well, does b have, did it say b has to
Is
be a
this-
constant?
yeah,
Oh. I thought b could just be anything.
okay, no, if they give a number like b, it's assume that b is a constant.
Okay.
All right, so that's number 37. How about 39 to finish this off? 39. 39. What is the 25th derivative of sine of x. Okay, any of the academic games people at Lanphier should chime in.
See, that's the funny thing too, is I was like, oh, I know how to do this, but it's been 2 years since
I
I've
just
done
found a
it.
pen.
Yeah, that's exactly what happens.
Cycling.
First of all, we're going to recognize that the first derivative of this, the first derivative of sine of x is cosine x. The second derivative, which would be the derivative of cosine, is negative sine of x. So the derivative of cosine x is negative sine. The third derivative, that's where we take the derivative of this again. Oops, bad notation. The derivative of what? The derivative of sine of x, and that's going to be negative cosine x. And then I do it again. The fourth derivative. Now hopefully I won't have to do this 525 times. Hopefully. Thank you for laughing. And then that is sine x. Now, when I take the derivative of sine x, I end up back at cosine, right? So this is the first derivative, but it's also the fifth derivative. This is the second derivative, but it's also the sixth derivative. This is the third derivative, but it's also the seventh. This is the fourth, but it's also the eighth. And if I continue doing this, another trend pops out. What's the trend that pops out?
Every 4.
These numbers on this one
Multiples.
are multiples of 4. So this is 4th, 8th. This is also going to be the 16th,
20th.
the 20th, so on and so forth. So what we want to do is, where do we end up close to? What's the largest multiple? Sorry, what multiple of 4 gets us closest to 725?
724.
724. 724 is a multiple of 4. So the 724th derivative is here. That means the 725th derivative is cosine. And that's how we do that problem. We see the cyclic nature of these derivatives and we exploit the pattern. All right? That's number 39. And I'm going to close this.